Okay guys, in this video we're going to work on sketching a graph of a polynomial that I suppose in general we don't really know what it looks like, but up until now we've been talking a lot about the characteristics of the equations of a polynomial and how they relate to the graph of a polynomial. So what I'm going to do is I'm going to give you a solid set of 4 steps here to follow when it comes to graphing a polynomial, but these are the same 4 steps that we always tend to use with any polynomial in general. So let's go ahead and start with the top here. If I want to sketch the graph of a polynomial, then I'm going to want to know some things about it, starting with what's the end behavior of our polynomial. So the very first thing we tend to always do when we make a sketch of a polynomial is to apply the leading coefficient test, and that is to say, determine what the end behavior would be here. So with respect to end behavior, we're going to write this in, but by recognizing what's our leading coefficient and what's our degree. So in this case, I recognize that my leading coefficient is positive. So with respect to the right-hand side of our graph, I know the right-hand side is going to rise. And because our degree is even, I also know that the left-hand side of our graph would have to rise. So as far as writing end behavior goes, we want to make sure that we do take the time to write it in this proper notation. But as our x values are going to the left, to negative infinity, what are our y values doing? It looks like our y values are then going to positive infinity. And as x goes to the right, or as x gets very large positive, we see that our y values are also rising on the right-hand side, are going to positive infinity. So we have our end behavior here. Next up, and I'm just going to go and put this on my grid here. It doesn't mean it goes through these arrows. It just means that on the left and right-hand side of my graph, I'm making a little indicator on my grid, on my quadrants here, that it's going to rise on both sides. So number 2 is going to involve finding the zeros of this function. And so we want to determine the zeros of this function. Well, the zeros are going to be all x values that cause our y values to be equal to 0. So we're going to start by substituting in a 0 for y. We're going to go solve for x. And as is the case a lot of the time with polynomials, it's just too difficult to get x by itself, so we're going to rely upon factoring. So in this case, and in every case when you factor, we're going to look for a GCF first, which I notice there are 3 x's that are common to both of these terms. So we get left with 3x minus 4 as our inner factor here. I notice this inner factor has 2 terms, but that it's not a difference of 2 squares. So we can't factor it any further. If that's the case, then we're just going to go ahead and take our factors and set them equal to 0. So in this case, we get x cubed equals 0 and 3x minus 4 equals 0. So in the first possibility here, we would add 4, I suppose, and then divide by 3. And so in this case, we get x equals 4/3 is one of our zeros. That's important to know. At the same time, over here, we could take a cube root of both sides, and we would get x equals 0. But I think that really kind of undersells what we're trying to say here, which is a 4th degree polynomial should have 4 zeros at most. So where are the other ones if this is just these 2? And so the fact is, I want you to understand that when you have x cubed equals 0, this is the same as x times x times x equals 0. And so this has itself 3 factors, or a repeated factor here, a factor that was repeated 3 times. And so we're going to get x equals 0 and 0 and 0. Another way to write this is to just say x equals 0 with a multiplicity, try that again there, multiplicity of 3, which means we got it 3 times. We also got x equals 4/3, and I'm going to say, just to note this here, a multiplicity of 1. Usually when it's a multiplicity of 1, we don't write that. We just assume it was once if you didn't write a non-1 multiplicity. So we've got our zeros here. What should I do with these zeros? Well, I should plot them, probably. So I know it hits at 0, and I know it hits at 1 1/3 here. So I'm going to put some notch marks on my grid. So say, how about 1, 2, 3, 4, 5 to the right. Make sure we label this here, 1, 2, 3, 4, 5. Now I'm not going to get carried away with my y-axis yet. I'm just going to take the time to make sure that at 4/3 right here that I put a 0 on there, and at 0 I also put on a 0. So as far as I know, this is all I know about this graph. It comes in from the left side, from up here, having risen on the left, through this point. Now I got this answer an odd number of times. So that means an odd multiplicity means it's going to cross at that 0. And it's going to go back through 4/3, which means it also has to cross there since I only got that once, and then end up on the right-hand side. So when you look at this 3rd step and it says plot a few additional points, what I'm going to recommend for this plot a few additional points, plot a few additional points. What I'm going to recommend then is that we create a table. So this is going to happen in a table. The other thing is this, we're going to plug in an x value to the right and left of any 0. So in this case, when we make our table, and I feel like I'm going to have to resort to doing it sideways, which makes me, it's painful. It's painful. I don't want to do it this way, but we'll do it this way. X, f of x. What I'm going to make sure that I put on here is that I have to have some x values to the left of this 0, and our first 0 happened at 0. So I'm going to put in -1 into my table, and you're going to notice also that I left myself some room on the left of -1 just in case I want to plug in, say, -2. Now to the right of this 0, but also to the left of this 0 at 4/3, we have 1. We could plug in a +1 as an x value here. So I would say +1 could go right there. And then I want to plug in an x value to the right of this 0 right here. And so maybe I'll plug in, see, 1, 2. And I'll leave myself some room on the right there. So for right now, I'm just going to plug in these values. And what I see is when I plug in -1, I suppose I'd have to show my work here. And I will. 3x to the 4th minus 4x to the 3rd. We have f of 1 is 3x to the 4th minus 4x to the 3rd. In this case, we get 1 to the 4th and 1 to the 3rd are both 1. We get 3 times 1 minus 4 times 1. We get -1. So it's good to know that at -1, our graph should be at a height of -1 here. If I wrote down my function carefully here, which I don't think I did, 3x to the 4th minus 4x to the 3rd, 3x to the 4th minus 4x to the 3rd. You know what? I made a mistake, and that was this. I plugged in a +1 here and here. So forgive me, -1 needs to go in right here when we plug in a +1 for x. Let's take a look at truly if I had plugged in a -1 for my x value here. What would we have gotten? So 3 times -1 to the 4th power minus 4 times -1 to the 3rd power. Let's do our exponents first. We get 3 times a +1 here, since we raised it to the 4th, and then minus 4 times a -1 here. So it looks like we get 3 plus 4. Looks like we're at a height of 7. Okay, so now last one we need to plug in, f of 2. I suppose we would get 3 times 2 to the 4th minus 4 times 2 to the 3rd. Doing our exponents first, we get 3 times 16 minus 4 times 8, which ends up being 48 minus 32, which comes out to be 16. Okay, so now something I want to mention about leaving myself room on this table here. I notice that my y values here, at least as I start to go to the right of this graph, should start to climb really high. And so at 2, we're already at a height of 16. It just means that I'm probably not going to have to plug in 3 because I know it's just going to be even higher than 16 that's leaving my graph. On the left side, however, at -1, we're at a height of 7. And I realize that it's supposed to rise on the left, and 7's just really not that far off the ground. So this would be at a time where it would be really appropriate, let's try this again here, to go plug in maybe an additional x value here. And I'll try to squeeze this in over here. What if I had plugged in -2? And so I would have gotten 3 times -2 to the 4th minus 4 times -2 to the 3rd, which would be, now let's see, 2 to the 4th would be 4 times 4 is 16. But here, -2 to the 3rd actually comes out to be a -8. And so what we get is this 48 in front plus 32, which is 70, 80. You guys, 80. So I'm still going to put that on my table, but what this goes to show is we could probably stop there because now I can see that my y values are climbing without bound. So if it looks like we can fit these y values on here, or try to fit these on here, maybe what I need to do is change my scale so I could fit some of these bigger than just going by 1. So this is 10. We'll make this 20. And so to sketch this polynomial, it would look a little bit like this, and maybe I'll switch out to a green finally here so we can really see it. We had our zeros, first of all, and so we found a few additional points. We're just going to go plot these points now. So -1, 7 would be at about right here. We have 1, -1. So if we're going by a scale of 2, that would be right about here. And then we also have 2, 16 would put us right about here. So with respect to what this function looks like, we know at -2 that y value is way up at 80. It just means that it's coming in real steeply here. And as it comes in real steeply, it turns, goes below, dips above, and then comes back out again, kind of like this. And so this would be our polynomial function. And so essentially when it comes to graphing these, every time, I'm just going to throw this out there again, we're going to start just by determining the end behavior and then locating the zeros on the x-axis. But once we have the end behavior and the zeros, we kind of just want to know what's the behavior of the graph in between the zeros and on the outsides of the zeros. And that's what our table is going to accomplish for us. Once you get your table made, we can decide on a scale for your y-axis. But go ahead and plot those points, and then to the best of our ability, we're just trying to graph a smooth curve from left to right through the dots that has the indicated behavior at those zeros and at those points. Cheers.